When we look up at the night sky, the stars seem calm and eternal, tiny pinpricks of light scattered across the darkness. But in reality, each star is a colossal powerhouse, a blazing sphere of gas undergoing dramatic changes over millions or even billions of years. The story of a star is one of creation, transformation, and sometimes, spectacular destruction. Let's begin at the very start of a star's journey, the stellar nursery. Deep in the vastness of space, enormous clouds of gas and dust float in silence. These regions are known as nebulae. Under the influence of gravity, parts of these clouds begin to collapse, pulling material inward. As the gas compresses, the temperature rises, and a protostar is born, a baby star still gathering mass. Over time, as the protostar grows hotter and denser, a powerful reaction begins in its core, nuclear fusion. In this process, hydrogen atoms fuse to form helium, releasing a tremendous amount of energy. This energy pushes outward, balancing the inward pull of gravity. At this stage, the star officially enters the main sequence, the longest and most stable phase of a star's life. Our own Sun is a main sequence star. It has been shining for about 4.6 billion years and is expected to continue for another 5 billion. But not all stars live the same life. The destiny of a star depends mainly on its mass. Small stars, with less mass than the Sun, burn their fuel slowly and can live for tens of billions of years. These stars often end their lives quietly, cooling down into white dwarfs after becoming red giants and shedding their outer layers into space. Medium-sized stars, like our Sun, eventually run out of hydrogen in their cores. The core contracts, and the outer layers expand, turning the star into a red giant. In this phase, the star may engulf nearby planets. When fusion can no longer be sustained, it sheds its outer layers, creating a glowing shell of gas called a planetary nebula, and leaves behind a dense white dwarf. But the fate of massive stars is far more dramatic. These giants live fast and die young. When they run out of fuel, their cores collapse under gravity. This collapse triggers a violent explosion known as a supernova, one of the most powerful events in the universe. The explosion can briefly outshine entire galaxies and scatter heavy elements like iron and gold into space. What remains can be either a neutron star, an incredibly dense core made of neutrons, or, if the star was massive enough, it collapses into a black hole, a region of space so dense that not even light can escape. But how do we know all this? How do we study objects that are so far away? This is where the science of spectroscopy comes in. When light from a star is passed through a prism or diffraction grating, it spreads into a spectrum, just like a rainbow. But instead of being smooth, this spectrum contains dark lines, called absorption. Using the powerful technique of spectroscopy, astronomers have developed a system to classify stars based on two key characteristics, temperature and color. This system organizes stars into 7 main spectral types, represented by the letters O, B, A, F, G, K, and M, a sequence memorized by generations of astronomers with the phrase "Oh be a fine girl/guy, kiss me." Let's break this down. O-type stars are the giants of heat and energy. They are incredibly hot, over 30,000 degrees Celsius, and shine with a bright blue light. These stars are rare but extremely powerful. They burn through their fuel rapidly and live only a few million years before exploding in spectacular supernovae. Next are B-type stars, also blue but slightly cooler than O-types, followed by A-type stars, which shine white. Then come F-type stars, with a yellow-white color, and G-type stars, like our own Sun. These stars are golden yellow, with surface temperatures around 5,500 to 6,000 degrees Celsius, and they live stable lives for billions of years. Following that are K-type stars, which are orange and cooler, and finally, M-type stars, the most common stars in the universe. These red dwarfs are the coolest and faintest, but they can burn for trillions of years, outliving every other type of star. This classification doesn't just help scientists identify stars, it also helps predict how they live, evolve, and die. Color and temperature are clues to a star's mass, age, and life expectancy, an astronomical biography written in light. But beyond the classification of stars lies a more mysterious and fascinating phenomenon, gravitational lensing. Now imagine this: light from a distant star begins a journey of billions of years, traveling through the vast emptiness of space. But it doesn't always follow a straight path. If it passes close to a massive object, like a galaxy, a black hole, or a cluster of galaxies, the enormous gravity of that object bends the light, curving it like a lens bends light here on Earth. This remarkable effect is called gravitational lensing, and it was predicted over a century ago by Albert Einstein in his theory of general relativity. According to this theory, gravity doesn't just pull, it actually warps the fabric of spacetime, bending the paths that light takes. Gravitational lensing can create beautiful, strange visual effects. Sometimes it creates multiple images of a single object. Sometimes it stretches distant galaxies into arcs and rings. But perhaps most importantly, it acts as a cosmic magnifying glass, allowing astronomers to see things that would otherwise be far too faint or too distant. Thanks to this natural magnification, we've been able to peer back into the early universe, seeing stars and galaxies from a time when the cosmos was still in its infancy. One of the most astonishing discoveries made using gravitational lensing is a star named Earendel, a name that means morning star or rising light in Old English. This star was discovered by NASA's Hubble Space Telescope in 2022. What makes Earendel so special? It's currently the most distant individual star ever observed. Based on the data, the light from Earendel has traveled across space for more than 12.9 billion years. Due to the expansion of the universe, its current distance is now estimated to be over 28 billion light-years away. That means we are seeing Earendel as it appeared just a few 100 million years after the Big Bang, a time when the very first stars and galaxies were beginning to form. This discovery opened a new chapter in astronomy. By studying Earendel and stars like it, scientists gain rare insight into the conditions of the early universe, a time of mystery, chaos, and creation. What were those first stars made of? Were they larger or different from stars we see today? How did they influence